Okay, this is not one of the suggested problems for this chapter. This is problem 455. But somebody asked us during the class, and we kind of answered it partially. We might as well just do this completely, because it's again, this is something very classic you can find in a lot of books, but it's a good example on how to work in the inertial frame rather than a non-inertial frame. So I sometimes tell that working in a non-inertial frame is going to be confusing. This is one of those cases. Usually it's not, but this is one of the cases where I think it is more confusing. All right, so we have a small block of mass m that's resting on a capital M, triangular block of mass capital M, which itself rests on a horizontal table as shown in the figure. Assuming all surfaces are frictionless, determine the magnitude of the force F that must be applied to M so that small m remains in a fixed position relative to large M, so that it doesn't move. So it's not sliding down. We're applying some force from the left. Okay. And I think you can imagine that if I push hard enough, this is not going to be able to fall down. Okay? In fact, if I push really hard, it's going to start climbing the incline. If I push too little, then it's going to go down. There is a sweet spot, and we are to find that sweet spot where this actually does not fall down the incline. Its height, so to say, remains the same. And so they're asking for this. External. What is this? And there's a hint. There's a hint. Take the x and y axis horizontal and vertical. So typically in an incline, we take this coordinate system. They are not telling us to take this coordinate system. Okay? Sure, why not? Let's take this coordinate system. Okay? Now, how would you approach this problem? Okay? So we can actually calculate this total external force in terms of some acceleration, or we can calculate the acceleration in terms of the total external force, because they are moving with common acceleration. Okay? They're moving together. So this external force is going to be m plus m times some common acceleration. This is something I know. Is it useful? I don't know. I don't know if it's going to be useful yet. All right, then I'm going to look at these individual parts. This by itself obviously does not help. And let's start by looking at the small mass. Okay? Now, what are the forces acting on the small mass? Well, there is a gravity, small mg, let's call this. And there's going to be a normal force acting on it. If normal, or if small m normal, because there's going to be normal acting on this one as well. And this angle is theta, and so is this angle, I suppose. Well, how do I find this? Well, I imagine that this is normal force, this is the incline. If I make the inclination angle smaller, this angle also gets smaller. So this angle must be that one. Okay? This is how I remember it. I know that it's either this one or that one. And as this one gets smaller, this one gets smaller, so it must be that one. Okay? Or you could just throw some nice triangles and do this by trigonometry. That's fine. And this is also theta. Now, how do we proceed here? Can we write, for example, let's just keep these Fg and Fn. Can we write Fn is equal to, Fg cosine theta? It is mg cosine theta. Can we do this? Now, what would happen if that was the case? When would this happen? Now, we always say that the job of the normal force is to stop an object penetrating into a surface. It just keeps it at the surface. So in this case, this component, Fg cosine theta, is going to be this component, it's that component. They cancel, so there's not going to be any acceleration in this direction. Okay? Is there no acceleration in that direction, though? In fact, there is. There is an acceleration going this way. Okay? And that acceleration certainly is going to have a component this way as well as this way. Now, it's not moving with respect to the incline, but it does have an acceleration along the incline as well as perpendicular to the incline. Now, that's because it has these accelerations. The incline itself also has those accelerations. Okay? So this is not going to work. This is wrong. And now the hint they gave us becomes useful, because in what direction do we not have the acceleration? There is a direction in which we don't have the acceleration. It's pushing this way, everything is moving that way, so we have an acceleration in the x direction, but no acceleration in the y direction. Nothing is moving in the y direction. Everything is moving in the x direction. So the net force along this direction must be equal to 0, and that means Fn times cosine theta must be equal to Fg, which is of course mg. Right, the cosine went to this side. Why? Well, because of physics. Because of physics. This is Newton's second law. The net force in this direction must cancel. Why? Because the acceleration in that direction is 0. And this is the cancellation condition. Fn cosine theta must be equal to mg. Now, what about the x direction? Well, Fn sine theta must be equal to m times a. Okay. Now, what can I do here? I don't know the normal force, but I can divide this side by side. Tangent theta is going to be normal cancel a over g. So a is g times tangent theta. So this must be m plus m g times tangent theta. And I express the external force in terms of the given quantities. Okay? This is an example of a simple but hard problem. Simple is not the same as easy. This is very simple. There is nothing here. Okay? I don't need to take this wrong step. You just throw one free body diagram, you write one equation, two equations, and then you put them together. This is very easy, but you have to think about the physics carefully. Okay? And this hint is useful. You could have done this without the hint. You could say, horizontal, vertical, and so on and so forth. All my acceleration is horizontal, so I'm not going to have any vertical force. So all the vertical forces must cancel, which means the vertical component of normal force must cancel with the purely vertical gravitational force. And you could proceed that way, but think about why they are giving the hint if you can't proceed. As I said, this is a little bit tricky, but otherwise it's simple. It's not easy, but it's a simple problem.